mulaikan dalam doa. Siapa yang akan pimpin doa? Oke, Kristi, silakan. Amin. Selamat pagi, silakan dulu. Sebelum kita mulaikan pembelajaran pagi ini, silakan mengambil presensi terlebih dahulu. Ya, tidak banyak yang hadir hari ini. Ya, tapi seadanya saja karena kondisi juga cuaca yang tidak bagus. 1, 2, 3, 4, 5, 6, 7. Oke, sip. Kita masih akan melanjutkan pembelajaran kita kemarin, ya. Jadi kemarin kita langsung belajar tentang fluida dinamis, ya. Pembelajaran kita pada hari ini, ya. Jadi apa tujuannya di sini? Melalui proses pembelajaran materi fluida dinamis, ya. Agak typo, terus masih seperti biasa pakai problem based learning, pakai pendekatan saintifik, dan siswa peserta didik diharapkan apa? Menerapkan sikap ilmiah. Terus dapat menerapkan ini hukum fluida dinamis ini pada kehidupan sehari-hari berdasarkan berbagai macam sumber. Kemudian diharapkan terakhir dalam diskusi kelompok dan dalam praktikum hari ini. Praktikum hari ini yaitu praktikum tentang Pipa Venturi, ya. Ini dia. Nah, menggunakan eksperimen serta mampu mengkomunikasikan dalam bentuk apa? Presentasi, hasil percobaan, dan pemanfaatan dalam kehidupan sehari-hari, ya. Nanti sebentar saya sudah menyuruh kalian kemarin untuk membuat alat Pipa Venturi, ya. Jadi, ya, nanti orang mau praktek sama. Nah, ada video. Ini video stimulus seperti kemarin penerapan hukum Bernouli, tapi Pipa Venturi. Apa sih insert? Nah, mari kita lihat bersama-sama.
Hopefully this looks familiar. I don't know about you, but this used to be a favorite activity of mine when I was younger. Usually because it included soaking my brother. But I always just thought it was some sort of garden magic and never really understood it. Of course, now I understand it's an embodiment of the Venturi effect, an effect that myself, Rob, and Ruan will try to explain for you now. So what we saw in the garden hose can be imitated with the simple diagram of a pipe constricting. If we imagine that the flow is constant and the constricted area is half that of the initial area, then the water flowing through this constricted area will have to travel at twice the velocity. However, this increased velocity results in low pressure or a pressure drop. This is due to the Bernoulli effect, which can be confusing to understand, so before moving on with Venturi, we will explain it to you with the use of another simple everyday example, one which you should be doing a lot more of these days. So if we think about this further in the simple diagram, the water runs down from the tap and hits our hand at a point 2. After that, it runs down the outside of our fingers. But at this point 2, that's where we feel most pressure from the tap, yet the velocity there is actually 0, it's stagnant. This proves our point that low velocity equals high pressure. Contrary to that, as the water trickles down our fingers, it has velocity, yet we don't feel any pressure on the outside of our fingers during this movement. So this kind of proves how low pressure equals high velocity. So to clarify, high velocity, low pressure, and vice versa. Now that Bernoulli's effect has been clarified, we can look into how the Venturi effect is applied in everyday life. In particular, the idea of a Venturi vacuum, where fast air flowing through a constricted area creates a vacuum effect. To understand how this works, we have another little example here. We see how blowing through a cardboard tube can create a vacuum effect, sucking up all the sawdust. How does this work? To understand it, we can have a look at this other diagram, imitating the experiment. So if we imagine the air from the gun traveling at 100 meters per second, and mixing with 4 times as much stagnant air that is just sitting in the tube. According to the conservation of momentum, the resulting airflow leaving the tube will be 5 times the initial air mass and therefore will travel at 20 meters per second. This previously stagnant air therefore now has increased velocity, which means lower pressure. The surrounding high pressure ambient air therefore rushes into the low pressure region, creating the vacuum effect. Rob will now take us through some topical examples of how this Venturi vacuum effect is used every day.
This is a Venturi mask, and it's something, unfortunately, we've all become far too familiar with since the outbreak of COVID-19. It's the only oxygen device capable of delivering exact percentages of oxygen, and fascinatingly, its working principle is the Venturi effect. So the breakdown of the mask is pretty simple. Oxygen is delivered to this tiny little tube at the bottom, and when the patient breathes in, the mask makes use of the Venturi effect by mixing the higher pressure surrounding air with the low pressure high velocity oxygen travelling through the mask. But the most important part of the mask is that little orange thing there, which is called the fixed orifice device.
We break this down to the parts of the Venturi mask that really matter. This little boot cap is the fixed orifice device with holes surrounding it. This red pencil represents the high velocity channel that the oxygen will experience when the user breathes in, and these green squares represent the surrounding air. So what happens is, when the user breathes in, the oxygen is sucked up at high velocities, creating low pressure up along here. Now where this really matters is inside the fixed orifice device, where higher pressure surrounding air is met with the lower pressure oxygen flow. So let's see what happens when a user breathes in. So the user breathes in and the oxygen is sucked along at high velocities, sucking in the higher pressure outside air like so.
Another application of the Venturi effect is a spray gun. This can be easily explained using a simplified diagram like so. As high velocity air flows through, this creates a suction. This suction sucks out the stationary paint from the reservoir, with the paint mixture leaving from the nozzle covering the object. The next application is a Bunsen burner, which is the basic principle of gas heaters in homes. The simplified diagram as shown. High velocity gas comes through the inlet, which creates a suction, which pulls in the air, creating a mixture that exits as a flame. In conclusion, the Venturi effect explains why there's an increase in velocity with a decrease in pressure due to the principle of mass continuity when a fluid flows through a constriction, and vice versa when there is an expansion. So there's a decrease in velocity as pressure increases.
Nah, ini Pipa Venturi, orang aplikasi bagaimana cara menghitung kecepatan di dalam apa? Di dalam pipa. Kalau ini kan ada 2 pipa, ada pipa yang kecil sama pipa yang besar. 1 kali, 2 kali. Seperti contoh penerapannya kalau dilihat terakhir sekali seperti lihat ini bukan tukang cat. Di sini ada pertanyaan? Jelas? Jelas. Oke, selanjutnya. Nah, di sini ada KPD seperti biasa kalian bisa scan dan ada KPD juga yang akan bagikan ya. Ini monitor alat yang seperti ya. Kondisi hujan tidak apa-apa nanti ya. 1, 2, 3 ya. Ya, ukur Jo. Dapat lihat tuh air?
Ya,
kelihatan tuh air?
Ya.
Kelihatan tertutup lagi.
Begini tuh sih.
Kurang.
Berarti ini tuh.
Ampere.
Begini tuh. Itu 1 tuh, H1.
Berapa senti?
Berapa sih?
10. Ini berapa?
Ini kan. Mana sampai dari mata?
Satu. Ya pada orang satu kedua.
Lah.
Oke, sudah. Lanjut ke berikut kelompok 2. Sudah apa? Simpang je. Sudah apa? Let's go masuk, Jo. Masuk.
8 meter.
Let's go masuk.
Hukum Bernouli atau Materi Hukum.
Ya.
Hasil dari kesimpulan yang kita dapat bahwa pipa pertama memiliki tekanan yang lebih besar daripada pipa yang kedua.
Baik, terima kasih para murid. Lebih besar dari V1. Maka tekanan pipa pertama lebih apa? Lebih besar pada dengan tekanan pipa kedua. Ya, itu syaratnya. Ya. Terakhir, sebelum orang tutup, siapa yang satu orang?
Kita pada yaitu kesimpulan tentang materi penerapan azas Bernouli terlebih khusus Venturi ya.
Terima kasih. Orang terus selesai lagi. Ya. Jadi, oke, sudah. Sampai yang bisa. Terima kasih, silahkan share di para grup. Ya, nanti mau bisa masuk. Ada. Sama kasih satu kali. Ya, yang kemarin punya sampai hari ini. Sebelum saya tutup ada